Okay, good morning, first of all, to all of you, the organizers as well as the participants. And first of all, I would like to thank QIQT, the organizers, for giving me an opportunity to discuss my research work on this platform. So I'll be talking today about how entanglement and non-local correlations are related to quantum games, or how they help the outperformance in quantum games. So I'll begin first with the use of entanglement as well as the concept of superposition in quantum games with simple examples of games. Then I would show an example of a quantum game which corresponds to a quantum cryptographic protocol, a well-known cryptographic protocol. And then I will show the representation of the Bell CHSH inequality in the form of a Bayesian game. So as we all know that the states which we can see on the right hand side, the phi plus minus and the psi plus minus, they are the Bell states, the entangled states. And if such states are shared between two parties, if their particles are shared between two parties, their measurement outcomes will be correlated. So as soon as one party measures the particle 1, if it collapses in, let us suppose if this is the state that Alice and Bob are sharing, as soon as the first particle collapses to qubit 0, the second particle will also collapse to qubit 0. And this is what we call the correlation between entangled qubits or between entangled states. Now, this kind of property of qubits or quantum systems can be exploited in different quantum information processing techniques like quantum teleportation, in super dense coding. These are the simple fundamental ones. Different cryptographic protocols like the QKDs, QSDCs, quantum dialogue, secret sharing, and key agreement. Moreover, this entanglement feature is also exploited in quantum algorithms like the Shor's algorithm, the Bernstein-Vazirani Diaz-Josa algorithm, and as well as today we will see its use in quantum games as well. So to begin with, I will just explain the concept of game and how do we represent that in the form of a payoff. So a game is nothing but any competition or any competitive activity which takes place between multiple players, and the award or the reward that the players achieve is represented in the form of the profit or the payoff. Now, let's take this example of a simple game. This is the Battle of Sexes game between two players, the husband and the wife. Now, the husband and the wife, they want to spend the evening together, but they have different preferences. So suppose husband prefers to watch the football match, whereas wife prefers to watch a movie that evening. So if both husband and wife go and watch the football match, it is the husband who gets the higher reward because he gets a chance to play, to spend the evening off with an activity which he prefers. Whereas the wife would have to compromise a little bit with a little lesser payoff. On the other hand, if both of them go and watch the movie, so this cell represents when both husband and wife watch movie, in that case, wife would get a higher payoff than husband. And if both of them go for a different sport, that is, if suppose husband goes to watch football match and wife goes to watch movie, then in that case, their motive does not suffice. That is, they were not able to spend the evening together. So both of them get a 0 payoff each. So this is how we represent games. This is nothing quantum about it. It's just a classical game representation in the form of a matrix. Now these games, this scenario can be used in different applications, starting from economics to political science, bio, computer science, as well as philosophy. And today we will see its use in physics as well. So another simple game where I will first show its classical counterpart, and then I will show how entanglement has enabled or how entanglement has helped to resolve the dilemma in this game. So this is a very well-known dilemma, prisoner's dilemma. Some of you might be familiar with it. So there are two prisoners who are suspected of committing a crime, and they are taken to two different cells where they are interrogated. And in their interrogation, they are asked to confess their crime. So they have two options. Either the prisoner 1 and the prisoner 2, they can confess. The C means that they can confess their crime, or they can deny their crime. So if both of them confess their crime, they get a payoff of 3 each. If both of them deny their crime, they get a payoff of 1 each. If one confesses and the other denies, they get a payoff of 0 and 5 respectively. So these payoffs means this is the reward that they are getting. So, and this payoff that I'm showing over here is like inversely proportional to the number of years of imprisonment that they get. So higher payoff means that they are going to spend less number of years in the prison. Now we can very easily find out, this is simple mathematics, that if suppose the prisoner 1 is the prisoner 2, if he fixes that he is going to confess the crime, then in that case, suppose if we look across the column 1, if prisoner 2 confesses the crime, then prisoner 1 will be better off by denying, because 5 is greater than 3 anyways. And similarly, if prisoner 2 fixes that he or she will deny the crime, then prisoner 1 again will be better off by denying, because again 1 is greater than 0. And this is a symmetric game, so that means it is the same for the other prisoner as well. And therefore we can conclude that the game, this scenario will tend towards that Alice and Bob, or prisoner 1 and 2, if they are taken to 2 different cells and they are interrogated, keeping in mind that they are selfish people, they want to achieve a higher payoff, and they do not know what the other prisoner is going to say, whether the other prisoner is going to confess or deny. Looking into that, this entire game of prisoner's dilemma will tend towards both the prisoners denying their crime. This one. Whereas we can see that both of them would benefit when both confess rather than both deny. So this is what the problem of prisoner's dilemma is. Although the Nash equilibrium is the deny strategy, the Pareto optimal, that is the better strategy, would be that both of them confess. That would be the common good move. Now, quantum strategies help us resolve this dilemma. That is, whatever Nash equilibrium we will get, that will also be Pareto optimal in case of a shared entangled state between the 2 prisoners beforehand. So this is a general setup of prisoner's dilemma game, where I have, instead of taking the numbers 3, 1, 5, and so on, I have taken R, S, T, and T as the variables. Now the strategy, now since we are jumping to the quantum version of prisoner's dilemma, the strategy, instead of direct confess and denial, it would be a 2-parameter set of 2 cross 2 unitary matrix that the 2 players, let us call them Alice and Bob now, the 2 prisoners, Alice and Bob, they can perform this strategy. Now this theta ranges from 0 to pi and phi ranges from 0 to pi by 2. So they have this whole set of strategies, 2-parameter set of strategies that they can perform. And the C and D that we can see, we have again used a set of theta and phi for to represent the classical confession and classical denial strategy. Now we begin in such a manner that the initial state is the CC, that is confess state, or we can also say that this is, to be simple, this is a 0, initial state, which is entangled with this unitary operator J hat. And after entangling it, Alice and Bob, they perform their respective unitary operation. They can pick up any theta and phi from that general 2-parameter strategy and apply those unitary operations. And thereafter, they will again perform J dagger and unentangle their state to get this psi F, that is the final state. Now, whatever is the state of this final state, that will determine the coefficient, or that will determine the probability that the state either collapses to CC, CD, DC, and DD. So since we have considered that this C and D, they are the 2 bases. Okay, so they will either collapse into CC, CD, DC, and DD. And depending upon that, we can find the expected payoff of Alice and Bob. The expected payoff of Alice and Bob would be the one which is shown in these 2 equations. This R, P, T, and S, these are the variables which were associated with the original prisoner's dilemma game. So as soon as we get a CC, that means Alice's payoff will be R times the probability that we get CC. And as soon as we get a CD, that means the probability gets added to the expected payoff. It is S times the probability that we get CD, and so on. Similarly, the same applies for Bob's payoff also. So that is what has been written over here. This is the expected payoff of Alice and Bob. For fairness in this prisoner's dilemma, there are certain mathematical concepts of commutation kept into mind, that this entangling operator should commute with the D tensor D, D tensor C, as well as C tensor D, as well as we have fixed a general entangling operator that we can use for this quantum version depending upon gamma. So there goes this entangling operator that we can use, where gamma ranges from 0 to pi by 2. Now I'm taking some generic values. So as soon as I take gamma equal to 0, it collapses down to the same separable game or the classical game that we had just seen. Because gamma equal to 0 means that we are performing an identity on that state, and therefore the denial strategy is the non-Pareto optimal Nash equilibrium. Whereas if we want to see the entangling effect on this prisoner's dilemma game, we can apply, or we can use this value of gamma as pi by 2 that will maximally entangle our prisoner's dilemma game, and we will get we will get different strategies. So now Alice and Bob, they have very wisely picked up one new set of strategy. Instead of confession and denial, they have also taken this Q strategy, where theta is taken as 0 and phi is taken as pi by 2. And we get this unitary operation. So after performing this unitary operation, they have a certain set of expected payoffs that they get. And if this payoff matrix is analyzed, we get that this Q cross Q becomes the Nash equilibrium. That is, the game tends towards Q cross Q. That is, Alice and Bob, if they are taken to two different cells, if they share some entangled states amongst themselves, they will perform this Q measurement on their operators, this Q unitary operation. This measurement they will perform respectively in their different cells on their qubits. Whatever result they get, be it that they have to confess or deny their crime, depending upon that, they will answer when they are being interrogated, and that will be a common good move, as well as that will be the Nash equilibrium also of the game. So this is a very good example. This was proposed by Isert et al. In 1999 itself. This is the quantum version of prisoner's dilemma. Now, over here, we analyze that this is how entanglement can help resolve dilemmas in games. Another simple example of a game would be not only entanglement, just a superimposed or superposition state can also help us in quantum games. This is again a very simple example of a game. This is Mayer's penny flip game. Now we have two players over here, P and Q. P places the penny head up in a black box. So there is a penny, it could be in the head up state or in the head down state. And we are considering that it is an unbiased coin or unbiased penny. The winning strategy would be that Q will win the game if upon opening the box, if it is found that the penny is still in the head up. We will begin with the head up state, and at the end also, if it still remains head up, Q will win. In between, what are the actions that Q and P can do? So Q and P, they can either flip or not flip that penny. Now first, P has that box in which the penny is placed head up. P passes the box to Q. Q can either opt to flip or not flip. So Q does not know what how the penny is. It just has the option. It can flip or not flip. Q passes the box to P. Again, P can flip or not flip. P passes back the point to Q, and again Q can flip or not flip. Now P and Q are unaware of what each other have done to the or what strategies they have opted when they had the box with them. So this is the only step that takes place in the game, and finally the box is opened and it is checked whether the penny is head up or head down. Head up hoga to Q wins, otherwise P wins. Now the classical version of the game, if we analyze, it is unbiased. In half the cases, P will win the game, and in half the cases, Q is going to win the game. And this is a zero-sum game because if Q wins, that means P has lost. So if I represent win with a +1, loss is represented by a -1. So this is the simplest version, the classical version. Now switching over to the quantum version. Now this penny or the coin that we have taken, this can very easily be imagined in the Hilbert space, in the two-dimensional Hilbert space. The head-up state can be imagined as the ket0 state, and the tail or the head-down state can be imagined in the Hilbert space as a ket1 state. Now, similarly, the actions that the P and Q players are taking, they can also be visualized as the flip can be visualized as the poly X operator or the spin flip operator, bit flip operator, and the not flip can be represented as the identity operator. Now, what extra has happened in this quantum version of this penny flip game is that P still remains the classical player, but Q has now become a quantum player. So that means P still will take classical moves, but Q has the advantage of taking quantum moves. Now, one very important unitary operation in quantum mechanics is the Hadamard operator. This Hadamard operator also creates superposition, as well as it also helps us create entangled states. Now, Q will very wisely choose to use this Hadamard operator. And what will Q do? As soon as Q's turn come, it will, instead of flipping or not flipping, it will perform the Hadamard operator. And so as soon as Q applies the Hadamard operator, it will take the head up state to a superposition of head up and head down state. P, when it flips or not flips, the state remains as it is. And Q again will apply the Hadamard operator and take back, since it is a reversible operator, it will take it back the superposition state to the head up state. And now what happens? Because the winning condition was such that when the box is open, it should be in the head up state. So it will be realized that it is still in the head up state and Q will win the game. So this is a game where in 100% cases, the Q, that is the quantum player, wins. So this very nicely shows the outperformance of a quantum player in quantum version of this penny flip game. Now, one can say that this is why the game is wisely designed such that the quantum player wins. Yes, it is such a design in such a way that the quantum player wins. And this is to showcase. So this kind of games are used to explain to students that how superposition in quantum helps us in outperforming the classical players, so that they are able to imagine and able to realize the powers of quantum computing. Similarly, this entanglement, which was used in Prisoner's Dilemma, it might seem a little trivial, but again, this is useful in explaining the fundamentals to students who are not familiar to these concepts. Now, coming back to the second thing that I wanted to discuss is that not only the superposition and entanglement helps us in quantum games, but we can also understand quantum cryptographic protocols using quantum games. So this is another game, a 3-player game, where we have Alice, Bob, and Charlie. Now this Alice, Bob, and Charlie, they are sharing this 3-party entangled state, the GHZ state. The game goes as follows. Alice, Bob, and Charlie, they will be asked either the X question or the Y question. So either all of them are going to be asked the X question, or 2 of them will be asked the Y question and 1 will be asked the X question. So ye question, what is this question? So it is a type of input that they have, and they have to give some answer to those questions. That is, they have to give some output to those questions. So basically the input is whatever question they are asked, depending upon that, they will perform measurement on their particles. So out of this GHZ states, A, B, and C respectively, these particles are shared by Alice, Bob, and Charlie. And suppose if Alice, Bob, and Charlie are asked the XXX question. So suppose Alice is asked, what is X? Bob is also asked, what is X? Charlie is also asked, what is X? So all three of them will perform a X basis measurement on their particles A, B, and C respectively. And depending upon whatever outcome they get, a +1 or a -1, that they will respond or that they will give as the answer. So suppose Alice gets a +1, Bob gets -1, and Charlie gets a -1. So they will return back those outcomes. Similarly, if they're asked question X, Y, Y, they will do the same thing. Alice will measure in X basis, Bob and Charlie will measure in Y basis and return their outcomes. Now, what is required as per the winning condition of this game is that their measurement outcomes should give us the product this. So whenever they are asked the XXX question, the product of their results outcome should be 1. And in all the other 3 cases, the product should be -1, right? So since the GHZ state has such correlations that whenever these questions or whenever these measurements will be performed, all the 4 cases or all these 4 conditions will always be true. So the success probability in this case would be 100%. But what if these 3 players are not sharing any 3-party entangled state? Without any entangled state, they would randomly give answers to these questions. What is X? What is X? X, what is X? And in those cases, even if they fix their answers, even if they, whatever strategy they apply, the maximum winning probability by any classical strategy or by any classical discussion that they have done beforehand, it will only be 75%. Whereas with the sharing of this GHZ state, the success probability increases to 100%. And this very nicely designed game has a correspondence to quantum secret sharing. So what is quantum secret sharing? Now, secret sharing is that phenomena where there is one sender who wants to send information to 2 players, but the sender does not completely rely on those 2 players. So part of the information will be sent to receiver 1 and a part of the information will be sent to the receiver 2. And collectively, both the receivers will have to cooperate with each other to get the entire information. So in that case, if one of those receivers, even if that person is a cheat, he or she will be caught and he or she will not be able to get the entire information by himself. So again, this quantum secret sharing begins with the sharing of that same GHZ state between the 3 parties. So over here, I have assumed that Alice is the sender who is trying to send information to Bob and Charlie in 2 different parts. Now, Alice, Bob, and Charlie are going to share this GHZ state beforehand, the A, B, and C particles with Alice, Bob, and Charlie respectively. And they will now, Alice, Bob, and Charlie, they will perform measurements on their states, either in the X basis or in the Y basis. Now, what happens? They will randomly choose their basis. So when Bob and Charlie, whatever basis they choose, they will announce and they will tell that this is the basis that we have chosen. So whenever Bob and Charlie choose the same basis X and X, in those cases, the measurement outcomes of Alice would be this. So that means if Bob and Charlie have chosen the same basis X, then Alice should also perform the measurement in the X basis. Similarly, if Alice, Bob, and Charlie have chosen the Y basis, then also both have chosen the same basis, then also Alice should perform measurement in the X basis. Now these pluses and minus are the outcomes that they get when they measure in this basis. And if Bob and Charlie, they measure in a different basis, that is in this case and in this case, then Alice should perform measurement in the Y basis. All other combinations of measurements, they are discarded. And again, we can see that the same set of conditions, winning conditions, which we saw in the Vedman scheme, they are a part of quantum secret sharing also. So again, to explain this very nice quantum secret sharing protocol to students, we can use the concept of Vedman's game. Now, I had also analyzed this Vedman's game for different set of questions or different set of strategies, and it was realized that the another class of three-party entangled state that we have, that is the W state. In that case, if we pick up a standard W state, and if we slightly modify our questions to in the Z and the Y questions, that is the measurement in the Z basis and in the Y basis, then the standard W state, it helps us achieve a little lesser probability of 87.5%. This is lesser than what we could achieve in the GHZ state, which had 3 tangle equal to 1. Now this W state is used because this is another class of three-party entanglement where the 3 tangle is not 1, but we have sigma, which is there in this state. That is another entanglement measure which we can use for three-party entanglement. Then another state that I tried for was the WN state, which was proposed by Agarwal and Pati, which is used for deterministic teleportation and dense coding. And that for n equal to 1, it gives 86.425% probability of winning this modified strategy of Vedman's game. Then I also plotted the winning probability with respect to their entanglement measures. So with respect to 3 tangle, as 3 tangle increases, the general GHZ state, its winning probability increases. Similarly, when the concurrence increases, the winning probability of the general W state also increases. And interestingly, we can see that this for the WN state, the W1 state, that is for n equal to 1, we are getting the maximum probability. Then we could also see that how does noise react on Vedman's game. So if there is presence of noise in this Vedman's game, then in that case, W state surprisingly was more robust to the in comparison to the GHZ state. How? Because the classical winning probability of this game was 50%.
Ms. Kaur, sorry to interrupt you. You have 2 minutes more.
Yes, I will conclude that quickly. Okay. So we can see that the W state is more robust because especially in case of the phase flip channel, phase flip noise. So in that case, the entire this green curve that we can see is very far from the classical winning probability, even though this noise has enacted on the channel. Okay, I'll skip this portion and I will directly come to the CHSH inequality. So we are all familiar with the Bell CHSH inequality, which goes as follows. Now, the winning condition of this game is that the outcomes of Alice and Bob, YA and YB, their XOR should be equal to the product of their inputs, XA and XB. And this XA and XB are random bits that a referee has distributed to them. Now, this can be very nicely put in the form of a Bayesian game. Now, what is this Bayesian game? So, we have the strategies of Alice and Bob, but their strategies would depend upon the type of the player. And the type of the player is this XA and XB. So whatever inputs that Alice and Bob were getting over here, that will determine the type of Alice and Bob. So they are of different categories. Now Alice can be of type 0 and it can be of type 1. Now, depending upon their types, their strategies and their payoffs would change. So in general, if I take up these utilities, that is, if I take non-zeros U1, U2, U3, and U4, and in these places, if I have a 0, this will represent the Bayesian game corresponding to the Bell CHSH inequality. And the following game, where XA.XB gives us a 0, this is the coordination game. And this game is the anti-coordination game, because coordination game similar to the battle of sexes game that we saw, because over here, both the players are trying to coordinate. Both are trying to perform the same strategy to achieve a higher reward. Whereas This anti-coordination game is the one where both are trying to anti-coordinate with each other. That is, both are not cooperating and doing the different acts in order to achieve higher payoff. Now, since I have lesser time over here, I will quickly conclude. So I have taken some of these values, and then we had analyzed that for the classical, there are 16 different classical strategies. So to avoid the mathematical complexity, I have ignored that slide. So there will be 16 different classical strategies, but in all of them, the total payoff does not exceed 2. But when there is a quantum strategy, then this quantum strategy is again the same, that Alice and Bob are sharing a entangled state between them. And in those cases, the sum of payoffs of both of them, if we write it in the mathematical form and if we break it further, it has this Bell's CHSH operator over here. And as we all know, the Bell's CHSH operator, when there is entangled state, when suppose there is a Bell state which has non-local correlations, the maximum value of it would be 2√2. That is, it would the Bell CHSH inequality will be violated. And because of that violation, we get to see a higher sum of payoffs of Alice and Bob in case of quantum scenario. And with that, I will conclude 3 important points that I tried to discuss over here. That entanglement as well as superposition both support quantum outperformance in quantum games. There is correspondence of quantum cryptography with their quantum game counterparts, which can help us understand and propose new secure quantum cryptographic protocols. And third point is not only entanglement, but also non-local correlations also contribute to outperformance of quantum players in quantum games that we just saw quickly with the example of Bayesian games. Okay, so that's it from my side.
Yeah, okay. So we are running out of time. So maybe 1 or 2 quick questions from the audience. You can unmute yourself or you can type in the chat box. I will read the questions to Ms. Kaur. Okay, so I want to ask a question. Maybe it might be a naive question for you. So you have in one of your slides, you have written 2 types of games: separable games and maximally entangled games. And you have given the choice of phi. For phi is equal to 0, you have separable games.
Okay, the quantum version of the game.
No. Yeah. No, in the I think I think on slide number 9. Slide number 9. Yeah.
Okay.
So here you have, depending upon the gamma value, you have 2 types of games: separable games and maximally entangled games.
Yes.
So how at gamma is equal to pi by 2, this game becomes maximally entangled? Can you elaborate a bit?
Okay. So when we use gamma equal to pi by 2, the initial state that we are taking, right, CC, after applying this gamma equal to pi by 2 j hat to it, we are anyways going to share the maximally entangled Bell state between Alice and Bob. So that is why we are saying that that is a maximal entangling operator.
Okay, so and what happens when this gamma takes the value in between 0 and pi by 2?
So that is also a entangled state, but that will not be a maximally entangled state. So that will lie like the cos theta 0 plus sine theta 1 So the theta value will not be, it will range between 0 to pi by 4.
Okay.
That is the same as that.
Okay, thank you very much, Ms. Kaur, for this.
Excuse me.
Yeah.
This might be a silly question coming from me, but I was just going to ask if quantum version of any game, does it can it always be like the winning percentage of it, can it always be maximized? And like what is the limit that the quantum version of games have? Like
So
if classical winning percentage is always like mostly less than quantum versions, right? So how long can we stretch it?
So the maximum stretch is 100% that we have seen. And so now these games are very wisely designed so that the classical player has no powers and the quantum player has the maximum power. I showed this slide where I tried to pick up some other state and I tried to change these strategies also. So this is after a lot of calculation that I have done. This is the maximum that I can achieve in W state. So in W state, this was the limit.
Right.
Right.
Okay.
I think that answers the question, or you are asking something else?
Right. Yes. Thank you.
Okay.
Okay, thank you very much, Ms. Kaur, for this nice talk.
Okay.
Okay, so, okay, thanks. So the next talk will be given by Rahul Pratap Singh. Rahul, are you here?
Yep, I am.
Okay, so Ms. Kaur, please unshare your slide so that you can share it. Okay, so the Rahul Pratap Singh was MS student at IISER Kolkata when I was there as a research associate. So he is very hardworking student, and currently I think you are in University of California.
Yeah.
Okay, so he did his MS from IISER Kolkata, and there he has done a very good dissertation project with Professor Prashant Panigrahi. So currently he is at University of California. So Rahul, go ahead and share your slide.
Okay. Thank you. First of all, thank you, Aradhya. And yeah, it's an honor to present in front of you as my senior and Professor Panigrahi. He's my mentor, and yeah, IISER Kolkata will always be my home. And yeah, thank you, Dr. Kaur, for your talk. I really liked the examples, and I will steal one point from there when I will present. So yeah, already apologize for that. Yeah, so what I'm going to do is tell you guys about graph theoretical quantum error correction decoders, and I will try to make it as short as possible. But whatever information I'm going to present is already at a GitHub repo, which the link will be at the end of the talk. So yeah, you can use it anytime if you want to, and go and see how the software, like how the package works, and use it on your own to figure it out. So yeah, first thing first is that anything in quantum error correction or simple error correction starts with repetition of information to save it. Like the classical example for that will be, when you are over a phone call and you want to answer someone, and the question is in a yes or no format, like you want to ask him yes or no, and the line is very noisy, then you say yes, yes, yes multiple times, and the other person might not get it first time, second time, but yeah, if you say multiple times, there are chances that they will get it correctly. So yeah, this system is actually majority voting. So this majority voting can also be written in a mathematical format, which is, on the right hand side, that if there is a p probability of error in the channel and you are trying to send your information that side, and p probability says that it will flip or it will change to the no if you're trying to say yes. So this is what is the probability will be, and this is the probability for getting incorrect information. Mathematics aside, this is a classical example, but yeah, what error correction decoder will be is more important here. So in this case, the majority voting which you did in your mind was the error correction decoder. And how you find out your result is like highest frequency, which one was the highest number of time repeated. And well, here it is a very low error situation. So yeah, nothing much, but yeah, let's see quantum. So yeah, as Dr. Kaur mentioned, like the importance of GHZ state. So why not test it? So yeah, if you test it in a normal quantum computer without any error correction, this is what you will get. Yeah, there should not be anything in here. It should look like this one, but yeah, looking different. It means like, yeah, too much error. So yeah, what to do with it? How to remove these error in NISQ is of basically moving from NISQ to forward. The route will include multiple things. One would be either you improve hardware or improve gate application or implication, to be honest, the perfectness of how perfectly you can implement a gate, or quantum error correction. So what will this error correction will be? It will be an logical system, like you are creating a new set of qubits from already physical qubits. So you are trying to create a logical qubit from the physical qubit. And the only requirement these physical qubits will have will be that these logical qubits will have that the two states on a logical qubit should be completely distinguishable. There should be no point that at which you can like basically miss that it's a 0 to a 1 or 1 to a 0. And yeah, it can also be used for benchmarking quantum computers, but I'm skipping this part due to the time. So yeah, yep. So the most important thing to test your error correction method is error model. So yeah, okay, I've heard any questions?
No, I think it was.
Okay, thank you. So yeah, a simple error model requires three things, three kind of noises. First is your measurement noise, second is single qubit gate noise, and third one is multi-qubit gate noise. Just these three things, apply them in whichever gate you apply, and you will have your simple error model. Can be created easily, and or here is the code. You can just copy paste it. Or if you want to go very real, but this is all about modeling. This is not about like using a real hardware, because like if you use real hardware for testing, it will be too much. But yeah, in case if you want to just test it, so the most realistic model you can get is actually you can take it from one of the IBM's processor using its fake version, fake Tokyo. You can see this one is present here, and how it can be extracted. There is a you can find a module on that one, which is already included in the package from which this has been created. Yeah, so QC is actually three-step process. You encode the data, you measure it, and then you decode the information. Encoding means you take an input, you take psi, you encode in some format, and now it stays on the quantum processor. Then you measure it in a sense that you do not destroy the original information, but find out some things in there. You can do it multiple times if you want to, or at once you also. So yeah, there are different kind of measurement possible which you can apply. And at the end, what you do is you decode from the measurement results. Decoding will require a decoder. So this will be the focus of my talk. But yeah, these above two processes are also important. So encoding. So no cloning theorem basically prohibits cloning in quantum systems. So what to do, how to create copies. Well, there is a thing in no cloning theorem, kind of a disclaimer in asterisk, that you can actually clone states which are orthogonal. So this is what is happening here. You get to any state you can you can break it in 0, 1. Here I've taken simplest state 0, 1. Assume it is normalized. For this case, I haven't taken the here to normalize it, but you can. So yeah, what will happen is you use this circuit, and this circuit will create any combination of A, 0, 1 into this system, where you have 3 copies of each inputs. And yeah, well, encoding bit is important, but so as encoding phase. So yeah, any phase can also be encoded in this format, where this state can be written as plus, so plus 3 encoding, or you can change it into a totally different basis, plus minus basis, and this encoding will work perfectly. And yeah, measurement. So there are types of measurement you can do. Syndrome measurement is, so ZZ syndrome is actually a way of saying doing parity check on bit encoding. So you check if you see here the syndrome measurement is for 0 and 1. If 0 and 1 are same, it will give you 0 in sin 0 response. And if they're different, it will give you 1. So you know that if there is 1, then one of those is something has happened here. From here to the point it is measured, that is here. There is some error in there. Same, you can do it for like rest of those 2. So you don't need to check for all 3. You do it in pairs. For 3, only 2 times. And yeah, you can measure it, and then you will know that there is something. After encoding, we assume that this part is done perfectly. So After encoding till measurement, there has been some error in between, which has caused this parity disturbance. So this is how you can actually measure it without destroying the actual state, so that you can do computations later on it. And same you can do it for face encoding. It's just like phase change, so not to worry, just use a phase change of basis change operation, and you will be good to go. Similarly, and these are actually, if you apply to Hadamard, they become this standard methods. Okay, so other is decoding, the most important one, which I focused on. So yeah, for two type of encoding, you don't need, first of all, two decoders. One decoder can do both, and basis change is the way to go for like converting one decoder to other one. Just after you measure, change the basis to get information for the face encoding, or vice versa. So yeah, how these decoders works, that's here. So if for this circuit, the ideal output should be this, and you read from right to left. So like this is how it goes: link qubit 0, link qubit 1 to here. All these three are code qubit 0, 1, 2. And yeah, so these two are actually syndrome 1 and syndrome 2. So this is link qubit 0, link qubit 1 first time here, link qubit 1, link qubit 0, link qubit 1 second time here. And these three are the logical measurements. And yeah, but so this is like two encoding, a logical 0 and logical 1. They are the two things that you need to first encode to find out a system which is totally separable. And this is like how it is represented, which I've said, but you can later read it. So it's like this. And this is what your output will look like after addition of a simple error. So many outputs, and only one of this is correct. Rest all is error, but yeah, you have to correct error, every error one, and add it to the original one, so that the ultimate sum should be 8912 theoretically, but it won't be. You will have some of them which will say 1, which is not correct. But yeah, for logical 0, they will say logical 1, and for logical 1, logical 0. Just the opposite of it. Yep. So after you get your output, which is this is just repetitive form of writing this, you need to process that. So for processing, it's easy. Just follow the arrows. So if there is this pointed arrow, it means just copy. So 0, 0 brought down, and then again arrow 0, 1 brought down. When you see a circular arrow, it means you have to compare, do a parity check. If when you see two arrows here, it means compare. If they are same, 0. If they are different, 1, and so on. So now your 3, 2, 2, 7 digit system becomes now 8. Not much, just one difference. And now after processing your first, this thing will look like this. Now you don't need to actually change every one of them. The module will do it itself. But yeah, before that, you need, like, basically converting any decoder or any decoded processed output, you need to first have a coordinate system if you want to convert it into a graph. So how this coordinate system goes is that 3 coordinates are needed for 3D. We will do it with 3D. Is X, Y, Z. X is basically which says where is the error. So like these, they actually form a coordinate system which tells you where the error is. X is like either in logical or syndrome, which is this 3 are your logical, and remaining 4 here are syndrome. So it will tell you like which one, logical or syndrome. Then it says which round. So your which round information is this is first round, this is this is first round, this is second round. So if it's syndrome, it will tell you first round or second round, and which one in the round. So it could be first or second, but the counting goes from 0 to n. So yeah, remember that we say 0, 1. Some nodes can also be result of 2 points, which is like, so you see this, it means 0 and 2 flipped 1, 1, and 0, 1 flipped 0. And when you add them, flip means incorrect makes a correct, and remaining 1 remains. So this is mod 2 addition actually. But the general thing is that a bit flips, it flips again, so it's correct. Like goes from 0 goes to 1 and comes back to 0. So yeah, it's right. Yeah, the last task is actually to match nodes in the graph. And if a node matches with the logical node, it means there is an error in logical node. And that's when you have to care about whatever is going on. Before that, matching doesn't matter. Until unless your logical nodes are untouched, you are happy. There is no decoding need to be done. But you need to verify that if that is the case. So yeah, there is some note I have taken care of. It's for the drawing I have made here. So since X can only take two numbers, 0 and 1, you can do for XY in 2D graph, you can actually represent YZ from the 3D graph, like this system. And if X is 1, YZ plus 2. This 2 will change given that how many numbers of qubit you will have, always n minus 1. But for this system, it's easy, and for the modular, it's automated. So no need to worry. Yeah, so this, what you see is the syndrome graph. It means it's a graph which contains all possible errors in the 3-qubit system. Whatever is possible, it's here. So it could be, and these are 2 logical nodes down there. These are the most important ones because they are considered correct nodes, and they are a complete logical system in their own, and rest of these needs to be matched. So if you go for one code, you can make, like for each of the string, you can make a graph. For this string, you have this graph, and this graph, you need to match it, but matching is not what it looks like. It should be minimum weight, but I know most of the people will think, 1 this good. No, that's not a right answer. But yeah, how you have to do it is this. First, start with creating clusters, excluding logical nodes. So you have to exclude logical nodes, means the bottommost 2, and then create clusters depending on distance between them. Then check that whatever cluster you have made has even number of nodes. If they don't have even number of nodes, merge 2 neighboring clusters. But if one of the neighboring cluster is a logical node, then logical node itself is considered as a cluster. So ultimately should have all even clusters. That's a requirement. And repeat this process until you have all the nodes, all the cluster with even number of nodes. That is what is required here. And this is how it is done. So if you see this first graph, exclude these 2, create a cluster, the above 2 will be in one cluster, and that's how they will be matched to. So yeah, this is the solution. And so everything, whatever I've said is actually on this GitHub repo. And oh wow, I made it before time. But yes, I will also like to show you how actually this worked. So let me show you this. So this graph, if you can see, epsilon is actually the distance I can take from one node to other node, which I can call its neighbor, so that they can form a cluster. So okay, yeah, so these actually change with epsilon, but you can see how logical errors are. So these are like error probability, how they are increasing with increasing epsilon. And the best one is this. So like you can actually test it. This is already tested for IBM Q Manhattan, but you can do it for, like, if you want to, your own code. That will be available here, cluster decoder on this repo. And yeah, have fun doing that. If there is any question, please.
There is a question in chat box by Devdutt Sharma.
Sure.
So he is asking how we can decode or convert quantum state from IBM notation to their binary form.
Okay. So yeah, actually I have it here. So what you see here is starting is actually IBM's binary form. This is how it gives you output. And the module is already, like, if you go to the GitHub, you can install that module. And this is how it can convert the system into processed format. you can, this is the process, but you don't need to do it manually. It will do it for you. So yeah, feel free. It's actually made for QuizKit. So yeah. Any other question, please?
Okay, audience, participants, any other questions, query? You can unmute yourself, you can ask by yourself, or you can write in the chat box. I think there is no questions. So your talk is finished, or you have to say something more?
Oh, I'm done. Thank you. Thank you very much. Thank you, audience.
Okay. Thank you, Rahul, for this interesting talk. Okay. So the next talk will be given by Arghya. So are you here? Arghya Mukherjee.
Hello.
Yeah, okay. So the next talk will be given by okay. So then the next talk will be given by Arghya Mukherjee. He did his PSMS from IISER Kolkata in 2020, and currently he is working as a project associate at Center of Quantum Information and Quantum Computing at IIT Madras. So Arghya, you can share your slide and go ahead.
Sure. One second. One second, just.
Yeah, okay.
Yeah. So is it visible?
Yeah, it is visible.
Sorry, one thing is written wrong here. It will be masking. So we are talking about quantum masking today. So let's say, uh, so masking is kind of like a hiding thing, data hiding thing, like the classical one. So we are going to talk about it in a quantum regime. So let's say, suppose we want to encode a single bit of classical information. Let's say 0 and 1. We encoded it in the states 0 and 1. So, and we want to encode it in two orthogonal entangled state. So the states are kind of like this. So then if we encode this map, so 0 and 1, they are already orthogonal state, and these two states are also orthogonal. So if we look at the both of the subsystems, this subsystem and this subsystem, so they don't have any information about the classical bit. So the classical information is quite hidden in this system. So we can say that it is spread over quantum correlation of encoded state. But the thing is, so it is very fine in quantum system to hide one classical system. Hide one classical bit into that. But is it also possible to have this thing of, hide the classical quantum system into another quantum system, kind of like that? So, or can we can the quantum information be hidden? So can the quantum information be hidden from both the subsystems and remain only in the correlation? So if so, then somehow the quantum information gets spread over the spooky correlation and remain invisible to both the subsystem and that they are possessed by the local observer. So we call this thing vaguely spookifying quantum information or masking of quantum information. So the question is whether it is possible or not. The thing is, so let us first define what is a quantum masking. So let's say an operator S. So we call the operator S as masker. So an operation S is said to mask quantum information contains in the set. So this is an Hilbert space, and this is one set that is situated in A. By mapping them to the states, let's say this is a state, and this one state is in the also in the ancilla. This will be the state of an ancilla. So we are mapping HA to this thing such that all the marginal states of psi k AB are identical. That is, if we take the density matrix of it, so the trace of the density, so if we take the rho, that is the trace of the density matrix, and rho B, that is the trace of the density matrix, partial trace of the density matrix AB, we have no information about the value of K. So the S, so the operator S that we have spoken about is called masker. And since this is a physical process, it can be modeled by an unitary operator US on the system A plus an ancilla system B, given by this equation. US from AK tensor product B. So this is the ancilla system, ancilla qubit, that is in the system B, and this leads to our masked state, that is the psi. And since this is a linear transformation, it preserves the orthogonality, and moreover, S can be masked information in a set of states. So let's say the set of states are AK, then it can mask the information containing in the set of whose density matrix can be expressed as a linear combination of the density matrix AK and so the density matrix of AK only. Okay. So furthermore, we can say that it is important to require that neither A nor B contains the information of the initial state. Otherwise, a simple application of the swipe gate will mask the information for A by simply transferring it to B. So this A and B, they should be like they should contain like they should not contain any information of the initial state. So there the question comes. So we already defined what is masking and what is masker. So now the question will come that uh, whether it is possible to mask any quantum state or not. The answer is no. We cannot mask any arbitrary quantum state, and it's a proof. The proof is given by Kavan Modi, Arun Poti, Ujjwal Sen, and Aditi Desen. So it's a very popular paper. Uh, the paper is called "Masking Quantum Information is Impossible." So, so they actually gave two theorems. Uh, so main two theorems. They are called no masking theorems. So no masking theorems are kind of like other no-go theorems, as Poti has also worked on that, like no hiding theorem. It's also like no cloning theorem or like no deleting theorem and all those things. So no masking theorem, first theorem of no masking theorem says that no masker can mask all the qubits in H2. So H2 means a Hilbert space of 2, dimension 2. And the second theorem is an extension of the first theorem. So it says that an arbitrary quantum state cannot be masked. So at first, uh, we are going to look at the first theorem. So there is a proof of the first theorem. So let us assume that there is a masker S that can mask all the states the in a qubit. Let's say a qubit will be situated in a Hilbert space. Let's say it is HA, and there are some orthogonal bases of HA. So let's say that orthogonal, that S masker S actually gives yeah. So let's say the masker S actually gives actually maps the orthogonal basis into some basis psi k in another another space, that is the like that is the Hilbert space H A cross H B, and H psi k are orthonormal. So this psi k, sorry, I forgot to write this down. So that psi k will be orthonormal. Yeah. So now let us have an arbitrary state. Let's say it is A. So A is written here as A1, sorry, alpha 1 0 plus alpha 2 1. And we are going to map it to psi. And psi is exactly this. Just remember the coefficient, see the coefficient. We are just going to change the basis state only. Okay. But not the coefficients. So the coefficients are the same as it was there. And exactly as we like we are going to, at first we are going to take it pure state. So alpha 1 square plus alpha 2 square equal to 1. So next, if we take the partial trace with respect to x, then of psi, then we can have a trace like this, right? And equation like this, where x and y are the, like, x will be a coefficient, sorry, a subset of a, and y, let's say if we take any other subset y, so a subset of b, then x is not equal to 1, because as we have said that a and b will not contain the information about the initial state. So this last equation this last equation satisfies the masking condition of masking if the off orthogonal terms. So what are the off orthogonal terms? These are the off orthogonal terms, right? So the off orthogonal terms vanishes, and I have written it over here that the off orthogonal terms are going to be vanished. So by an arbitrary alpha 1 and alpha 2, this implies that this thing is going to be 0, right? So the thing is that this above condition, so this above condition, what we are going to show, that this is not satisfied uh, for any arbitrary quantum qubit, or any arbitrary alpha 1 and alpha 2. So to prove this, we will use a result, or that result is actually shown in this paper. So this is a very nice paper. You can go and check it out. So in that paper, actually this type of state was written kind of like this. So we use the information and we have written it expressed psi 0 and psi 1 like this, where mu and nu are not necessarily normalized and not mutually orthogonal as well, while mu and nu, sorry, like mu and this mu dash, I mean mu orthogonal, so they are orthogonal to each other, and uh, we will work with this. So let us compute the partial trace with respect to b. So b is the ancilla state. So let us compute the partial trace with respect to that. So they will be kind of like this, these three equations over here. So now if we then if we add the condition at this this into one second into these equations, we will get this thing. Okay, and this expression value of the this expression, I mean with respect to mu, this expression will give another expression, that is this, the expression following. So now using the equation that is given here, so now if we add the equation, I mean if we apply the equation, this equation to this equation, we will get another expression, that is this. So this implies, as they are not mutually orthogonal, but this and this are mutually orthogonal, so this implies that this is exactly equal to this, or this is equal to this, right? So the latter part will be a contradiction, uh, because this cannot happen. uh, yeah, so since they are not mutually orthogonal, so this cannot happen. But the former case, we can have, like, if we, let's say, if we have new orthogonal is equal to, let's say it is kind of like a state like e to the power I phi, so where phi is the phase of that, e to the power I phi nu, then we can have a expression of then we can have a expression that is exactly like this. And this last equation means that either mu is equal to 0 or orthogonal of mu is equal to 0. But if so, in either case, the state in the state that is defined by this equation, so the state that is defined by this equation, uh, that will not be entangled state. So there will not be any correlation, right? So implying that the state AB can be simply swiped, as we have talked before. So this is a contradiction. So therefore, an arbitrary state cannot be masked. So in that paper also, the in that paper, the paper written by Modi, Poti, and Ujjwal Sen and Aditi Sen there. So in that paper also, they extended it to another theorem, they generalized it to this theorem that an arbitrary quantum state cannot be masked. So we have proved it in for H2, and then there is another thing, not me, like they have proved it, and then they also extended it to this thing. But so the question generally comes into the mind that whether, I mean, cannot we write any, like, is there any set of or any class of quantum states that we can take it to correlations or not? The answer is, unlike the other no-go theorems, the no-masking theorem is not that much rigid. So the answer is yes, we can. It is possible to mask some particular class of the states, and there are the states of quantum. I mean, there are the sets of quantum states whose information we can mask, which contains the continuous and contains non-orthogonal state. So the continuous state can be masked, and non-orthogonal state can be masked as well. So in that paper also, like, they have shown that it is possible to mask quantum information if the quantum states are kind of like this. Okay, so see these states in a careful way. So these states actually belong to a family of states on the great hyper disk, and these are the extremal case of that great hypergraph. Sorry, hyperdisk, right? Hyperdisk on the block sphere. So we can encode the state, or we can mask the state, or we can take it to the correlation, and they are the continuous one as well. So with the information encoded with continuous parameter phi k, they are the continuous ones as well. So let's say there is a masker that takes this state k, so this basis k to kk. Then that masker can take this state psi, that is exactly this state, to some masking state that is psi. So this is a theorem also, and they have proved it in the paper. I am not going into that because I don't have, I think, a much time left. So think about this, like, so the thing is that if we take any class of states, so any class of pure states or like mixed state on a hyperdisk of any hyperdisk on a block sphere, that can be masked, and there we can find a certain masker for that. So that is the whole point of it. So naturally, one question should come into the mind that whether can we use it for any future purpose, or like for any purpose or not. So with the word masking, the first thing in the classical world, with the word masking, the first thing that comes into our mind, that is some data that is hidden somewhere, and only the authorities can access that thing, and the particular authority and the owner can access that thing, right? So one of such cases is the Aadhaar card, where your eyeball prints and fingerprints, all those are there in a masked situation. But with the help of the quantum computer, I mean, it is very easy to access those mask thing in mask thing of classical computer. So it will be better to have a masking thing in quantum computer as well. So sorry, one second. Yeah. So we can have a bank locker kind of thing, or some centralized cards like Aadhaar kind of thing with use of quantum masking. So it will be kind of like, so there is an idea of ours that we can take, let's say there is a state, so we can take our classical data to a quantum states, and those quantum states will be the pure states, mainly the pure states outside the hyperdisk. So let's say it's the equatorial hyperdisk on the block sphere. So we are going to take it to there, and then we have to find a masking, a masker, and there will be a centralized authority also. So the authority will be there, and so the authority will have a key, and the state of the authority also will be masked there, and the whole state, I mean the whole state, the peers and the authority, they will create some they will create a entangled state, entangled kind of state, so that is to take the whole state to a correlation, and they will be masked there, and with the help of the both the authority and the particular peer, we can access the locker. So that is kind of like an idea we are working on. So it's the whole thing about the presentation. So that's it. Thank you.
Okay, so we have 5 to 7 minutes for the questions or discussion. If anyone want to ask the question or any comment, you can share it. Yeah,
See,
Pandey sir want to go.
yeah, I have a very small question, for Arghya. Arghya, so this masking is only based on then orthogonality, no entanglement involved, right?
Orthogonality, no, like it is based on correlation. So mainly, yeah. So for for two-party system, it will be an Bell state.
Now, why I'm asking, because there are these orthogonal states without entanglement. So remember those, correlation without entanglement, purely based on orthogonality. So if it is purely on orthogonality, because I saw what you have implemented is only orthogonality, isn't it? So maybe one can think about it. I'm not very clear myself.
So orthogonality, yeah, orthogonality, it will be there, but it is, I mean, vaguely to speak that it is just to take some orthogonal state to a non-orthogonal state.
That is true, but again, it is, orthogonal, right? I mean, you are not using any other kind of quantum correlation, isn't it? Except Hilbert space structure, right?
Yes, that's true.
But I am not saying I have to think about it very clearly, because there are states which are not entangled but yet orthogonal. If you remember, those 2 by 3 kind of states which are by construction, that kind of thing. People are looking at, like Srishti Agarwal and some Subra, others, right? Entanglement, orthogonality based kind of thing, which is correlated but not entangled. So basically, I want to understand what kind of quantum correlation is behind masking. Very simple question.
So that is also a very tricky question, I will say, or not actually explored in that sense, I will say rather.
I agree with
because
you.
because also, like, 1 second, my laptop is hanging. Because if we see this state, okay, so if we see this state, this kind of looks like a GHG state, right? But in GHG, it is not exactly kind of like a GHG state, but this kind of like a GHG state. So it is not, I mean, for if we take the three-party system, so then it will be a kind of looking like a GHG state. So if it is a two-party system, then we have already seen that a
Right.
Bell state is enough,
Right.
right?
Right. Right.
So this
Right.
is, I think, this is also like about. I mean, there is a confusion also. Like it is
Yeah.
not
Yeah.
clear, and yeah. So, but exactly
Yeah.
what type of
Yeah. Yeah.
yeah.
Yeah. Yeah. Yeah. Very nice. Very nice. You gave a very good example. That's true. Yeah.
Thank you.
Okay. Yeah.
Okay, any other questions? Okay, so thank you, Arghya, for this very nice talk. So now you can unshare your slide.
Mhm.
So yeah,
Welcome.
just one more question, I think, from Arnav Chatterjee.
Yeah.
Arnav?
Yes,
Yeah,
sir. Good
yeah,
morning, sir.
yeah, please ask.
So actually, the point I was asking is like suppose this concept of masking of quantum systems.
Mm,
Suppose I have a
mm,
data set, like I have an image, and I want to hide some information in that, something like a steganography or something. So then, suppose there are two informations are there. So then, how the correlation will be applicable to hide the information? Suppose if I entangle those two qubits in a message and one data set, and if I create an
mm.
entanglement or some correlation, then after measurement, how I am so sure that the two states will be, I can get the exactly same two states. Otherwise, what will happen in measurement case? That can be lead to different result. The core, the message state and the base information state, the cover image, I can get the two different results as well. So how you can say like the it is perfectly information is perfectly available in the when I am getting the
So
reverse.
you are so basically you are asking that I know the my state, I am
Hmm.
just encoded it, and I know in what state it is encoded.
Hmm.
But if let's say I want to decode it from there,
Hmm. Yes,
so
yes.
what will be the thing, right?
Hmm. Hmm. Hmm.
Yeah, so it's a very good question actually. So the thing is where we are stuck here actually, that is the decoding thing only. The
Hmm.
thing is you pointed out the exact same thing, that after the taking the measurement, like
Hmm.
we are taking it to a correlation, right? So after taking the measurement, the whole correlation will be lost, right?
Yes,
So
sir.
the thing is
Hmm.
that we are actually thinking about this. So we are planning to have an like ancilla qubit. So add another ancilla qubit, and so let's say we are taking a measurement out there, and
Hmm.
so after that thing, the ancilla qubit will help us to rebuild the state again. So we are
Okay.
thinking about this again, thinking about this, but the only problem with this thing will be there will be too many states. I mean, too many qubits in there, and
Hmm.
that's why the whole system will be too much noisy.
Yes,
So
sir.
that will be a very big problem in it.
Something, sir, you are
So
like
that's
saying
why
something having some quantum memory. Like it will store some previous information and it will match those states or something like that.
kind of like that.
Hmm.
Yeah, kind of like that. Not
Hmm.
exactly, but kind of vaguely, yeah, kind of like that.
Hmm. Okay, okay.
But the thing is again, so it will like make the things more complicated, and the more
Hmm.
complications arrive, the noise will be more,
Yes, sir.
and the whole system. Yeah.
Okay, sir. Thank you, sir.
Uh, okay, so let us thank the speaker once again. Uh, so the next talk will be given by Mr. Subhash Shankar Pandey. Subhash, are you around?
Yeah, I'm around.
Okay, so you can share your screen. So Subhash did his master from Central University of Jharkhand, and then he came for his master thesis to either Kolkata, and which he has finished under Professor Prasant Panigrahi. And his main area of research is quantum computation, quantum information, and machine learning. And currently, he is working for a Canadian company as a research associate. That company is named as Cogniframe. So, Subhas, go ahead and share your slide.
My screen visible?
Yes, it is.
So, thank you for the nice introduction. And I must start with quantum advanced encryption standard. So quantum advanced encryption standard is just cipher that plays a critical role in advanced encryption or in field of encryption. So there are basically two types of encryption, that is symmetric and asymmetric. Advanced encryption standard is a symmetric encryption system that are widely used in all of the encryption that what we are talking around. This encryption system is also a advanced encryption system that is advanced AES 256, I think. Yeah. So this is a very well proven encryption system in classical field, and we are trying to put that on a quantum, or putting this in a way of quantum, so securing it with law of physics. This so let me give you a short introduction of what AES encryption is. So AES encryption is named for advanced encryption standard, and it is the most secure encryption system that available right now, a symmetric encryption system. And what we are trying to do, we present a hybrid quantum circuit for AES encryption using supervised learning classifier, and we predominantly employs single qubit gate, and the protocol is very modular in nature, so that we can add or more qubit and put it on AES 256, and it is currently available for available for NIST devices. We can put it on a NIST device, and the effect on this protocol is very minimal. So that is not going to disturb the system, and it can be in real time NIST devices. So I use three NIST devices for my experiment, that is IBM ARMOC, IBM Manila, and IBM Perl. Four different images. So let me give a brief introduction of what AES encryption is. So AES encryption start with add-on keys, and it has predominantly 4 steps. That is substitute by crypto and mixed column and add-on key. So how to start? So we have a raw information, and then we take a pair of key. That the information size of information is 128 bit, and the size of key would be the same, 128 bit. But we have to do a image key expansion, so that we could expand that 128 bit of key into pair of 44 different 128 bit key. So then when we start, we have to add first key on that information, and then we apply 4 different steps, that is substitute by crypto and mixed column as an add-on, and we have to do this 4 step 10 times for AES 128, and for AES 256, I think that is 14 times. This is how AES encryption flowchart look like. And to decrypt the data, we have to inverse all the steps, and we get back the information. As it is a symmetric encryption system, so we have the same key for encryption and decryption. So the next step is we will look each step and how is the step of AES encryption work. So let's start with substitute byte. So substitute byte start with there is a X box. S box basically is a pair keep is a matrix that have unique values that may be of any kind. For different encryption systems, the S box have different values. It not always come with same values. So what we do here is we substitute the information with the value of S box, and how we substitute the value of how we substitute the information with S box is basically depend on the information. So what the information would be, that completely going to help us on choosing the S box element. So the next step would be the shift row, and this shift row method, what we do is we shifted the row of each information. So it would be like that let me give you. If we have information of I1, I2, I3 like that, then we will shift each information to next row like that. So this step only shift the information, nothing more it does. In next step, we have mixed column step. So what we do here is we uh, this is a very crucial step, and this alter each and every byte of column and, and produce some different column or a new set of columns. So here we only mix the the first column or the previous column with different column. So this work like that. So then we have add round key. So in add round key, we don't do anything. It's just XORing the information with the key. This is all about the add round key. And now we have understand each and every step of this AES encryption. We follow each round 10 times, and we have a very encrypted information. So main purpose of doing AES encryption is it provides us a very scrambled data, and there is no signature of information in the encrypted data.
Subhash, your voice is not audible. I think there is some technical glitch. Subhash, are you around?
Maybe he's disconnected. Eh?
Yeah, I think so, sir. Subhash. Okay. So let us wait for a few minutes, maybe. Yeah, please.
Hello, am I audible to all?
Yes, you are audible. Please share your screen once again.
So am I completed all those things that AES steps? I don't remember where I cut off. So I think I've completed all the steps of AES encryption.
Yeah, I think you were at this flow chart of AES, probably on this slide.
So that is how it works. So I have discussed all the steps of AES encryption, that is substitute by septo and miss column and add round key. So we have to put that on 10 round to encrypt data. And the main purpose of doing AES is to scramble all the data in very nice way. So we have used three different type of key. We cannot call that key because we have a substitute byte S box and a mixed column element. We cannot call them as a key, but that work like that work like a key. So we have three different type of element that completely going to add on information, and we have a different type of set of key that we get from any asymmetric encryption system that may be of RSA or anything. We don't read on that, so that is not. We can do any we can use any asymmetric key. So this symmetric key is basically used when we have basically used on SSL, where that is a layer between transport layer and application layer. So as we are using a Zoom meeting, so we have application layer that you can see the screen that must have my screen presented on that. So that information is going to transport with a transport layer. That would be a Wi-Fi or anything, that mobile internet or anything. So we have to keep a layer between them, and on that layer we will encrypt the information. So if my screen information is going to you, that will be encrypted in between them. And to encrypt that, we have to first share an asymmetric key. So asymmetric key is being shared all the time. You have a asymmetric key pair shared between you and me. So that's not an issue. So you use that asymmetric key and encrypt that using AES encryption, and just we have a complete encrypted channel and no one can see what we are talking about. But uh, the RSA encryption uses all the prime numbers. So if you pick all the prime number of 256 bit, that is not much. That obviously is less than the total number of 256 elements. So we can apply a brute force on that. When we're applying the brute force, we can get the information using that brute force. Obviously, you cannot apply the brute force using your own computer. You need a very big supercomputer for that. But that is a doable thing. That can be decrypted using brute force. So our purpose is to break that flow, break that flow on the ACE encryption. So what we have done, we replace the channel with classical channel with quantum channel. So no one can encrypt it because we have the rule of no cloning theorem in quantum. So we cannot clone the information. Once you measure the information get destroyed. So you cannot do anything on that. And even if you decrypt the information, you get the information, the receiver will know that the information is tampered because he don't going to get the information. So it is completely secure. So once let me talk about how our encryption system start with. So let's say we have an information that is in type of image I have. We can have an information any format. That just boundaries of 128 bit boundary. So here we have information in this nice way, and then what we have done is we pick a theta from 0 to pi, that is 16 theta, that is completely equally separated from each other. When we then break this information into pair of 4 and 4. So this image is now converted into sample of 4 and 4, and we replace each 4 byte of information with a theta. So now we have 32 theta in that, and this 32 theta represent this image. So after information encoding part, we generate the key. So key generation basically done here by uh, quantum computer, because quantum computer can produce a best best random number. Whatever random number you are going to get from the classical computer is a pseudo random number. That is not completely random. That's so random just because that repeated after a very long time. But that's not completely a random number. Suppose if I have a coin and if I toss my coin, so either I'm going to get head or tail. So that is completely random. But if you look on that, that is not a random thing. If someone calculate the angular velocity that we are going to apply on that coin, and the air drag, and the surface on which it's going to fall. So basically, after a long computation, you are going to get that coin is going to give you head or tail. So that is seem to be random just because we cannot measure that. So, but here what we have done, here we take a hand market and measure it, and then when we put a hand market, then we put a qubit into a plus state, that is a completely superposition state. Then after measurement, we are going to get 0 or 1. That is completely random. No one can calculate that. That randomness is based on law of physics. So this is how we get a pair of 128 bit random number. Then in this side, I just want to show you how our information and key are represented. So this is the 32 theta that I have, that I represented at theta 1, theta 2, and like 32, theta 32. And this is our information. And then just like that, we get a key. And we after getting the key in a string of 128, we just repeated the information encoding part that we have done classical or information encoding part. So likewise, we get 32 theta as a key, and then we have a S-box. S-box is just a random UGET, and that have theta 1, theta 5, and lambda values. That is completely random or anything you can pick. So that is not the case. After doing that, we have to expand our key. For doing key expansion part, what we have done is we take all 32 theta and just shifting the theta value to another box. So in next step, we have K1 right there, and all the step are going to upright ones. Second theta is going to be applied that row wise. This is how we get key of 11th pair, because we need 11 key, 11 pair of key for each step, and one for first background key that we have here. So, yeah, for each round we need a add round key. So for each round we need a new pair of key, and this add round key also need a pair. So total we need 11 pair of key. So that's why we need to expand our key into 11 pair. And now we have 11 pair of key and 32 the theta, and how we are going to get that information is like that. First of all, we put a qubit into a superposition state, and then put a phase on that. That is our theta. This is how we encoded our information. And then for add round key, we just put theta on each gate. That is K1, K2, or whatever that key matrices have. So after that, we have substitute bytes. For substitute byte, what we have done here is we just put a you get on that qubit, and that is going to substitute that information into a uh, new state, and that is how we get substitute byte. And for shift row step, we just apply a swap gate on that. After applying the swap gate, we just get the shift row case done. And for mixed column, we just again put that state into superposition, or just we apply Hammond gate on that. And then I applied the gate we have get from mixed column matrices, that is M1, M2, M3. That is just a random theta that you can pick anyone, any set of that's not in case. So after mixed column state, then again we have put that add round part, that is applying the phase gate on each qubit. And likewise, I have to then 10 more sound. The information is now encrypted. We have a very new quantum state that is completely random. That is not actually random, but that seems to be random for anyone who measure it or to try to do anything with it. So measurement is not going to give you anything about the information, because you need to measure all in all case, that is x basis and y basis and z basis. Then only you going to get information about the whole quantum state. So you have a very few qubits that have the state, so you cannot do that. And now how we are get back the information, because our step is not end up on encrypting the information. We have to get that encrypted information again into classical field, because we are trying to use that as a layer, QSSL or SSL part. So we have to get back the quantum information to classical information. And that is the very crucial part in this interesting system, because getting the information back in using this quantum computer is a challenging task, and that's why we don't use any entanglement in our case. What we are doing is that when we apply a phase gate on that, uh, if we measure that qubit, we are going to get the superposition of 0 and 1, and according to the phase, the state or the amount of superposition is different. So for 0 phase, we are going to get all 1 state or all 0 state, and for 5 we are going to get all 1 state. So this is how we are going to reinvert the quantum information to classical information. So for that, although we are going to use a niche quantum computer that is noisy, so we have to take care of that noise. So we, for this case, what I have done, I trained a model using by taking all the quantum state and measuring it. So each time you measure the quantum state of, suppose I have 16 different theta. So I measure 50 times all the 16 different theta. So when we plot that, this look like that. So we can build a classifier or a linear classification of that. That is going to help you on classifying the theta or getting back the information. So this is working 100%. This is going to give me 100% accuracy because we have a fine line, or we have a sufficient space for classifying that data. So this is how machine learning part plays it. So, and then I pick 4 different images that look like that, and after encrypting that image, the encrypted image look like that. And then when we try to decrypt the image, the decrypted image look like that. So we are completely able to decrypt the information 100% right. We don't have any flaw on that. Information is completely different. And one more thing, the machine learning model that you have trained on a same quantum computer is going to work on same. Means you cannot pick train a model on different quantum computer and applying on different quantum computer, because each quantum computer has different noise signature on that is not going to work. So it is very specific. We have to train model for all the quantum computer that you are going to use. Then this is how the encryption and decryption work on this. That's all from my side. If you have questions, then you can ask.
Okay, thank you, Subhash, for this nice talk. So from the participants, any question, query, comment? Okay, so let us thank Subhash once again. Okay, thank you, Subhash. Please stop sharing your screen.